Welcome to my video course on mastering ERTMS ETCS signaling systems. Today, we're diving straight into a truly remarkable piece of engineering. We're talking about the Radio Block Center, or RBC for short. It's basically this central digital conductor that safely orchestrates high-speed railway traffic. And as you'll see, it's absolutely the core of the modern trackside ecosystem.
Okay, let's look at our roadmap for this explainer. We'll start with an introduction to the RBC. Then we'll cover its core functions and governance. After that, we'll unpack the architecture, look at how it generates movement authorities, and finally, we'll wrap up with the handover process.
Section 1. Welcome to the RBC, the heart of the system.
So let's start with a macro-level view to see exactly where the RBC sits within the broader ETCS Level 2 ecosystem. Think of the Radio Block Center as the safe central trackside computer system. It's essentially the heart of the entire ETCS Level 2 setup, completely responsible for the security of all trains running in its area. The crucial takeaway here is that without this digital brain, the whole concept of Level 2 interoperable cab signaling, it just wouldn't work. It literally replaces traditional wayside optical signals by moving those signaling concepts straight into the driver's cabin interface.
Section 2. Core functions and governance.
Now that we know what it is, let's look at what it actually does out on the railway. 70. That's a key number to remember, because it represents the typical maximum range in kilometers for an RBC. An individual radio block center manages the exchange of data required for safe train travel and separation exclusively within its own area of governance. So any train operating within that 70-kilometer footprint is strictly under its jurisdiction.
Within those 70 kilometers, the RBC has absolute, total authority. Every single train automatically reports its exact position and direction of travel right back to the RBC at regular intervals using the GSM-R radio network. This continuous stream of position reports allows the central system to maintain a flawless, real-time database of the track layout and the exact traffic on it. It uses all of that data to supervise and ensure the safe separation of every single train operating on the line, making absolutely sure no two trains ever occupy the same block.
Section 3. The RBC architecture. Underlying interfaces.
To really grasp how the RBC handles all this data so securely, we have to break down its underlying architecture. Now, you might be wondering, how exactly does a central computer safely bridge the gap between the physical trackside infrastructure, like switches and routes, and a high-speed train in motion?
Well, the answer beautifully illustrates the modularity of the whole system. The RBC itself is the safe central computer, essentially the core processing unit. But it depends heavily on a few key interfaces. First, it relies on the interlocking interface to figure out route availability, route occupancy, and the route state. Then, to actually talk to the speeding trains, it uses the NTG, or Network Transmission Gateway. The NTG is a crucial translator that converts the RBC's instructions into the GSM-R protocol. That's the wireless language used to broadcast securely through the radio network directly to the trains.
Section 4. Movement authorities. Generating safe paths. Okay, so with the communication channels established, the RBC can get to its most critical task, telling the trains exactly where they're allowed to go. This happens through a really strict logical sequence. Step 1, the RBC receives the verified route status, like occupancy and state, from the interlocking. Step 2, it receives and validates the precise position and specific braking characteristics directly from the approaching train. And finally, Step 3, it combines all this real-time data to generate a safe path. Through these steps, the RBC dynamically issues a safe movement authority, ensuring the train's specific physical characteristics are fully compatible with the exact portion of track it's about to enter. What's really fascinating here is how the ultimate result of all those RBC calculations is actually visualized. You get a clear, highly secure path assigned to a specific train. The RBC continuously calculates and updates these movement authorities, constantly sending transmission updates that dynamically incorporate static speed profiles, gradients, and route data as the train moves forward. It's like a perfectly choreographed digital dance.
Section 5. The handover process. Crossing boundaries.
Of course, a train's journey rarely ends within just one single 70-kilometer zone, and that brings us to the absolutely crucial process of crossing boundaries. When a train approaches the edge of its current RBC's territory, a highly synchronized handover process kicks in. This involves two distinct systems: the handing over RBC, which is the system the train is leaving and the one responsible for initiating the data transfer, and the accepting RBC, which is the system the train is entering and that must seamlessly take over supervision.
This digital handshake actually triggers a few kilometers before the train even hits the physical boundary. Both of the adjacent RBCs start exchanging critical train information in the background. The whole thing is meticulously designed to ensure a completely seamless transition. Because of this, the driver and the train experience zero loss of performance or speed. The train just keeps hurtling forward at maximum operational velocity, totally unaware of the complex data transfer keeping it safe.
So, what does this all mean? Well, it all goes back to a foundational rule of railway safety. Trains cannot collide with each other if they are not permitted to occupy the same section of track at the same time. This simple truth has been the goal since the 1850s. But today, the RBC flawlessly automates it on high-speed lines using continuous data streams, complex algorithms, and wireless radio, rather than manual stopwatches and physical signals.
It's a real game changer. But looking ahead, you have to wonder, how will the radio block center evolve as we push the limits of rail capacity and transition to even faster, denser network technologies? It's a massive, fascinating engineering challenge. As we leave you to consider how this vital digital conductor will adapt to the even greater demands of future railway technologies, thanks we can see in next video.